Okay, friends. Today we are going to study Heisenberg uncertainty principle. तो मैं थोड़ा सा इसके बारे में बताऊंगा जितना मुझे पता है. So let's see. Um, First, I will try to explain what this quantity is in this famous expression means, and then we will go to some intuitive example from the Griffiths. So to understand it better, right? The So what you see here is actually three para three letters x, p, and h cut, where h cut is a constant, right? H cut is a constant. It is actually an inequality. It is not an equation. Actually, it's an inequality. So, and on the right hand side inequality, you have a constant. On the left hand side, you have two variables x and p. X is what? X is position, and p is momentum. And then you have the symbol delta. So delta is a mathematical way of measuring, of calculating standard deviation. Standard deviation, and it appears a lot in statistics actually. And from where the standard deviation, um, let me explain what the standard deviation is means. So what you are actually doing, delta x means you are actually calculating standard deviation in x, right? Standard deviation in x. So standard deviation in x means, so first of all, you mean there is a deviation in x, right? So there is deviation in values of x actually. So it means there are a lot of values, like there are a lot of values of x, and you are just quantifying, or you are just calculating how much these values actually deviate from some standard value, like from deviate from a mean value. That's what that's how you calculate standard deviation. Not going into the details, that's very easy. There is a formula, specific formula to it. That formula you can search. It is denoted by SD is actually um, SD is actually square root of summation of x minus mu square divided by n, if I'm not wrong. Yes. Yeah. Yes, exactly. Summation of x minus mu square upon n. So this is standard deviation. So the point is, you have lot of values of x, and you are measuring how much of these values deviate from this mean position actually. How much there is deviation. Let's say this is delta x plus delta x, and this is minus delta x, right? Let's say you have 2 centimeter value of x, and then it's you're not sure if it's 2.2 centimeter or 1.6 centimeter. So it falls in a range of values. So that's what x you're measuring. Calculate standard deviation is x. Then you are also calculating standard deviation momentum. The good old momentum we know, the mass times velocity from Newton's law. And you are calculating the standard deviation in momentum. So it means there are a lot of values, there are a lot of range of values in P, right? And then you are calculating standard deviation in those values, similar to this expression. And the good part is, the product of these two standard deviations is actually a finite number, gives you a finite number, a constant. Always is always going to give you a finite number. That what it tells. It always going to, it can never be zero. Actually, the other way to say it, it can never be zero. It is always going to be a finite number. And there is a limit, there is a lower limit to that number. That lower limit is actually h cut by 2, and the maximum it can go, like, you into infinity, because it's right. The maximum it can go to infinity. So there is a lower limit to this number, that is h cut by 2, and h cut is of the order of 10 raised to minus 34. You might say this is very low number, but it is some finite number. It is not 10 raised to minus 35. It is 10 raised to minus 34. It's not 10 raised to minus 60, right? It is some finite number. And actually, it is, so other way to say is it's not zero, right? Let's say, um, let's say you have delta x equal to delta x very small. You are saying almost zero. So almost zero, we used to say it tends to zero or approximately equal to zero, kind of 0.0000 something. So then to satisfy this inequality, obviously you have delta x 0.000000 something 0008. Then you are multiplying, you have to multiply it with very 8. Let's say you have to multiply with very big number to get to a finite number, right? Only then, um, so the point is, to get a finite number on the other side, if you reduce one number, if you take delta x to very small, then your delta p, the other number, delta p has to be very large. So other way to how mathematicians used to say it, they say if delta x tends to zero, then the delta p should approach to infinity, right? Only then you get a finite number on the right hand side. So that's what Heisenberg uncertainty principle mathematically says, right? And what it um but now I want to give you some intuitive picture. Actually, it's from the book of Griffiths, and what it says, yeah, it, you might wonder like where it is. Like first to give you a background about this picture. Here you see a wave kind of pattern. So you might ask me why we are choosing a wave, right? Um, the idea is Heisenberg uncertainty principle. Actually, where you really see it, you see Heisenberg uncertainty principle. Actually, the main domain of applicability of Heisenberg uncertainty principle is atomic systems. In atomic systems, the real magic of Heisenberg uncertainty principle comes to the fore. So in atomic systems, like in an atom, right, there is there's something very weird happening that physicists used to say wave particle duality. Wave particle duality. And Heisenberg uncertainty principle gives kind of mathematical meaning to this wave particle duality. Yeah, it's kind of mathematical meaning to that wave particle duality. And as you can see, there is something, this Heisenberg's uncertainty principle is somehow related to this wave wave type of motion or wave, right? So it's kind of a particle who is going in a wave type of fashion. It's very weird to imagine for in first instance, but we can literally understand it from just a, not even a not from just a wave picture where it is coming from. And that's what Griffith has tried to explain in his book. So imagine you are having a rope, right? And you're trying to give it a you're trying to generate a wave type of pattern from that rope, and that rope is of like some finite length. He has taken his 50 feet, right? And what happens, you may happen to generate this wave type of pattern, and then you continuously shaking it, right? So that this wave is there all the time. So now I ask you, like, what is the wavelength of this wave? You will literally tell me, okay, the wavelength is just the separation between two peaks, right? Or separation between two valleys. That's the wavelength. Easy to answer. But let me ask you another trick question. So wavelength we know. The trick question is, what is the position of this wave? The position of this wave actually is hard to say, right? This wave is present at all locations, at all times, at least for this 50 feet distance. It's present at all locations. So you don't know where the wave actually is. The location, or we call it position, is actually unknown, right? You know one thing for sure, but you don't know the other thing, right? Similar kind of notion happening in the Heisenberg uncertainty principle. Let's go to another scenario. Let's say you happen to generate a different pattern. Now this time, instead of a full wave, we just generate one bump kind of pattern, and then it travels. When it travels, you capture a screenshot, you capture it with the camera at some point, and then you ask, what is the position? Very easy to answer. If I look on this graph, it is around 25 feet, right? It's around this location. The position is known. Now you know the position. Now again the trick question comes. What is the wavelength? Right? Wavelength is hard to answer, man. The wavelength you For wavelengths you at least need two consecutive bumps, or one valley, two consecutive valleys. Only then you are able to measure the wavelength or calculate the wavelength. Wavelength is unknown. And now you might ask me, okay, sir, but Heisenberg uncertainty was between position and momentum, but not between position and wavelength, right? It is really position and momentum thing happening, because there is another expression, very famous expression that you guys have seen somewhere. It is called de Broglie expression or de Broglie expression. Don't go into my pronunciations. Um, so wavelength is actually directly related to momentum. So now you can see, even in this picture, simple picture of a wave being produced by a rope, you can see, knowing position, you don't know about wavelength or momentum, and knowing momentum knowing momentum or wavelength, you don't know about position, right? The same kind of notion that we studied in the that we see in the Heisenberg uncertainty principle. So it's very visual in uh, if you go to the wave uh, world, or if you observe it in yeah, with the real world waves. Okay, next we'll try to see a practical example of it in optics. That's also very intuitive.